This is the transformation exercise package, which I'm about to solve, so I'll just start with number 1 right here. Okay, so number 1, consider the graph of f shown below. On the same grid, sketch the graph of f of negative x. So f of negative x is, as you know, is a reflection across the y-axis. So I'm going to draw this in green. It's going to be like that, and it's just going to be a reflection like that, because it's just a reflection across the y-axis. All right, so that's 1a, and we can move on. So now in this part, we can see that the following 4 diagrams, we just have 4 images. This is not the question yet. This is just information under F. So there's some 4 transformations. So let's just go to the next, let's see what the question is. All right, so complete the following table. Horizontal, so description of transformation, and we have to put the diagram letter. So there's a horizontal stretch with a scale factor of 1.5. So if we go back, this is the original diagram. So a horizontal stretch of 1.5, which means that it's greater than 1, so it would stretch out in the x direction. The y's would stay the same, it would stretch out in the x direction. So we can see that over here, for example, A, the y's are not the same. In B, the y's are the same, but it's moved to the right by 1, so it can't be B. And if we look at C, we see that there's more of a stretch, so 1.5. Let's just see if that's true. So for example, if this point is 2, 1.5 should be 3, so this point should be 3, and then 4 times 1.5 should be 6. So let's just see if that happens, and yes, that's 3 right there, and that's 6, so most likely it is C. It can't be D, because D is being moved up by 1. So for example, this one is C, and maps F to F of x plus 1, so this is a vertical translation up by 1, and the only one of these 4 that is a vertical translation up by 1 is diagram D. So because we can see that it's just been moved up by 1. So this is D. Okay, so give a full geometric description of the transformation that gives the image in diagram A. So let's look at diagram A. So if this is the original, and we want to find the geometric description that goes from here to here, so let's just take a look. Let's look at this point 4, 1. Right, this point right here. We can see that there's been no stretch because it looks exactly the same. So it must just be a translation. So this 4, 1, this 4 point has been moved all the way to -2. So in other words, it's moved to the left by 6, and then it's being moved down. So this point, it's 4, 1, and finally moves to 4, -1. So in other words, it's being moved to the left by 6, and then it's being moved down 2. So left 6, down 2. So the full geometric description would be a horizontal translation to the left 6 units, and a vertical translation down 2 units. And if I had to write this as sort of a function or of some sort, I would write f of, since it's to the left, so it's x plus 6, and then it's down 2, so -2. So remember, when it's left, this is plus, and when it's for the vertical, it's just down. So that's how I would write it. You're not expected to show this. You're just expected to give a geometric description. So this is sufficient. All right. So let's move on to number 2. Number 2, we can see. Okay. So the graph of the function y of x, this is some graph. Write down the value of the slope of the function at x equals 1. So at x equals 1, which is right here, this line here is relatively flat. And it's not relatively flat, it is exactly flat. So the slope of anything that's flat is 0. So in this case, m equals 0. In fact, don't write m. Maybe I shouldn't have written m. Just write 0. The slope is simply 0. Now, the slope of the function at x equals 3, so it's right here. Is x equals 3, and if we look at this line, if we look at the rise of the run, this is a run, or it's down 1 and to the right 2. So in other words, and we can see that it's negative slope, right, because it's going downwards, so it's -1/2, and that's the slope for this part. So B, on the diagram below, sketch the graph of y is equal to 3f of -x. So let's go to the original. And let's just get. One way to do this is sort of get the xy plot. So let's just get some main points. I'm just going to get 3 points over here. I'm going to erase a little bit. So I'm not going to get that point or that point. I'm just going to get those 3 points because that should be sufficient. So the xy plot in this case is 0, 1, 0, 1. This is 2, 0. Oh, sorry, 2, 1, 2, 1, 2, 1, and then finally 4, 0, 4, 0. So let's get this right here, copy, and let's do that here, edit, paste. Oops. Okay, for some reason the others didn't come, but that's okay. I remember the numbers. It's 2, 1, and 4, 0. Oops. Let me just move this here. So, oops. Okay, so let's go with numbers again. So it's 2, 1, and 4, 0. So if we look at this transformation. It's a vertical stretch of 3, and it's a reflection across the y-axis because it's negative over here. So really, what that means is negative x over here, and then 3y, right? So all we have to do is just, follow this basically. So negative of 0 is 0, negative 2 is negative 2, negative 4 is negative 4. Okay, 3y is 3, this is 3 again, and that's 0. So let's look at this. So 0, 3, 0, 3 is right there. Negative 2, 3, negative 2, 3 is right there. And negative 4, 0 is right there. And that's our graph right there. So that's what it would look like. And if we look at the original, it kind of makes sense. So first, it was reflected across the y-axis. And then it was stretched up by 3. So, and that's what we notice right here. Maybe I should just make this a little bit closer. So there we go. So that's 3 of f of negative x. Let's do this one. Here we go. So this is f of 2x. So once again, let's just get the original xy. The original xy was, I believe it was 0, 1, 2, 1, and 4, 0. So if I do this, this means it's a horizontal stretch by a factor of half. So in other words, all the x's are just scaled by half, but the y's stay the same. There's no vertical stretch or anything. So this is going to be 0, 1, 2, and this is 1, 1, 0. All these are divided by 2, which is why we have 0, 1, 2. So let's do this. So basically 0, 1 is right there. 1, 1 is right there. 2, 0 is right there. And so we just connect those dots. Yeah, and that's basically what the graph looks like. All right, so we're done with C. Let's move on to the next part. Okay, so in the diagram below, we have this function. Consider the 5 graphs in the diagram A, B, C, D, E. Okay, well, there's that. Which diagram is the graph of f of x plus 2? So this is the one where if we observe, it's to the left 2, because it's x plus 2, so it's to the left 2. So if it's to the left 2, if that's the original graph right there, the only one that looks like it's been moved to the left, and since this is 5, this should be moved to 3, and the only one that looks like that is D. So that would be the answer to this one. So this is D. Let's look at which diagram is the graph of negative f of x. So negative f of x, that's a reflection across the y-axis. So the only one that I can see that is a reflection across the y-axis, so in other words, it will flip around. So this flat part will be there and it'll look like that. The only one that I can see is C. Because if you observe, if you compare C to the original, it's flipped across the x-axis. So if it's flipped across the x-axis, that's what it would look like. And so this is C. And which diagram is the graph of f of negative x? So this is a reflection across the y-axis. And the only one, once again, that looks like a reflection across the y-axis is actually A right here. So if you observe these two, this is at 0, and then all of these are negative, so it's a reflection across the y-axis, so that's A. So that's A. Okay, let's move on to the next one. All right, so the graph of y is equal to f of x is shown in the diagram below. For each of the following, draw the required graph. So I'll just do it the way that we've sort of done it. I mean, you can sort of interpret this as well, but better safe than sorry. So let's make an xy plot. So this is 0, 0, 1, 1, 3, negative 1, 3, negative 1, and finally 4, negative 1. Okay, so if we're trying to do 2f of x, it means all the y's, it's a vertical stretch in the, it's a vertical stretch by 2. So all the y's get stretched by 2 and x stays the same. So it's 0, 1, 3, 4. And all of these become 0, 2, negative 2, negative 2. Okay? So all we have to do is now plot that. So here's 0, 0, 1, 2, 3, negative 2, and 4, negative 2. So all we have to do is just connect that, and connect that, and then connect that. So as we can see, it's sort of a vertical stretch by 2. You can obviously use a ruler and make this a lot straighter. Because I'm just doing this freehand, that's why it looks the way it is, but it can obviously be a lot smoother. Next one, which is y f of x minus 3. So basically, let me just get an xy plot again. So this is 0, 0, 1, 1, 0, 0, 1, 1, 3, negative 1, and then 4, negative 1. And what we can see, since it's x minus 3, what it means is it's moved to the right by 3. So all the x's get actually added by 3, not subtracted, but added. And then the y's stay the same. So let's just write the y's because they're sort of easier to do. And then if we add 3 to these, this becomes 3, 4, 3 plus 3 is 6, and 4 plus 3 is 7. Okay, so 3, 0 is right here. So now we're just plotting this. 4, 1 is right here. 6, negative 1 is right here, and 7, 1 is right. Oh, sorry, that's 7, negative 1. That's 7, negative 1 is right there. I just copied it wrong, that's why. So we go there, we go there, we go there, and basically, as you can see, compared to the original graph, it just really looks like it's being moved to the right by 3. Okay, so the point A3, negative 1 is on the graph of f. The point A prime is the corresponding point on the graph of negative f of x plus 1. Find the coordinates of A prime. So once again, you can just do this by a simple xy, but instead of plotting everything, you just use that original point, so 3, negative 1. And this is a transformation. So as we can see, there's a vertical stretch, there's a vertical reflection across the x-axis, which affects the y's, and there's also a vertical translation. So the x's aren't affected at all, it's just the y, so it's negative y plus 1. So x stays the same, and negative of negative 1 is positive 1, and 1 plus 1 is 2. So it's 3, 2. Let me just double check that. Negative y, negative 1, so 1 plus 1. Perfect, yeah. So it's 1 plus 1, which is 2, and that's our solution. So the coordinates of A prime is simply going to be 3, 2. And we're done. Okay. Let's go to the next one. Here we go. So the diagram below shows this is our function. Let h of x equal f of negative x. Sketch the graph in the grid below. So before I sketch it, observe that f of negative x is just a reflection across the y. So in other words, I can just draw an xy. Let me just do the xy plot, I guess. Here's an xy plot. This point is negative 2, 2, negative 2, 2. This point is a 0, 2. This point right here is 2, 0. And this point right here is 4, 4. 4, 4. Okay? And if I switch the x and y's, not switch the x and y's, but this is f of negative x, which means that there's a reflection across the y-axis, which affects the x's. But the y's stay put. So all I'm doing is multiplying all the x's by negative 1. So it becomes 2, 0, negative 2, negative 4. But the y's stay the same. So it's 2, 2, 0, 4. And basically, I just have to graph that over here. So it's 2, 2, 0, 2. So it's 2, 2, 0, 2. If I go back up further, it's negative 2, 0, and negative 4, 4. So negative 2, 0, and negative 4, 4. Right, and basically now I think I should just use a ruler here just to be safe. So basically it will be that, like that, and then like that. So as you can observe, it's just been reflected across the y-axis, and that's what it looks like. It just looks exactly like a reflection across the y-axis. Let's go back here. Now, let g of x equal to half f of x minus 1. The point 32 is on the graph, then it's transformed. Find the coordinates of p. So again, we can do this the same way as we did before. So we have xy, which is 3, 2, and we want to see what the transformation is. So basically, we can observe there's a vertical translation, there's a vertical stretch by half, and then a horizontal translation of 1 to the right. So this becomes x plus 1, and for this becomes half y. All right? So this becomes 3 plus 1, so it's 4, and half of 2 is 1. So the point of p, so basically p, will simply be 4, 1. And this is our solution. Okay? All right, so let's look at this. The diagram below shows how the graph of y equals x squared is transformed to the graph of y equals f of x in 3 steps. For each diagram, give the equation of the curve. All right, so here's y equals x squared. And what they're saying is it goes from a to b, maybe let's scroll down a bit. It's going from a to b to c, and there are certain transformations happening. And basically, this is f of x. So it starts from y equals x squared and ends up with this function over here, which is y is equal to f of x. So let's take a look for each diagram below. So as we can see, here's that. And really, they only do one transformation at a time. They don't like combine them. So you're going from here to here, and as we can see, it's really just been moved to the right by 1. So the way we write this is y equals x minus 1 squared. Okay. Another way to do this is, if you're confused about how I got that, another way to do this is, now we can't call it f of x because they told us that this is actually f of x. So let's just call it g of x. So let's call it g of x is equal to x squared. Okay. So if g of x is equal to x squared, then this must be g of x minus 1, right? And it's g of x minus 1 because it's been moved to the right. And if you remember, all we have to do is we have to just take this argument and plug it in right there, right into the x, because that's what g of x is. So if we do it that way, then this is simply equal to something squared, and that something has to be the argument, which is x minus 1. Okay, let's do this. As we can see over here, that now, from this diagram to this diagram, the 1 stays put, but there's a stretch. The 1 goes up by 4. So in other words, all the y values should be multiplied by 4. So if it gets multiplied by 4, then this simply becomes 4x minus 1 squared, right? And it's 4 because this is a vertical stretch. As you can see, it's been vertical stretch. So 1 times 4 is equal to 4, and so that's how we get that. And then from here to here, we can see that it's just actually been shifted up by 3. And we know it's shifted because 4 plus 3 would be 7, and 0 plus 3 would be 3. So this final graph is 4x minus 1 squared plus 3, and that's how we do it. So this is for that one, this is for this one, this is for this one, and finally this is for C. Okay, so let's do this. Number 7. Let f of x equal 3x squared. The graph of x is translated 1 unit to the right and 2 units down. The graph of g is the image of the graph of f after this translation. Write the coordinates of the vertex of the graph of g. Okay, so one thing is, now this might sound confusing, like write the vertex? Like how do we do that? So it's really, really helpful to sketch things out. So here we have f of x is 3x squared. So in other words, I'll just sketch it here. So 3x squared, you should know what that looks like. It looks like this. Okay, it's basically like x squared, just like a parabola, but there's a vertical stretch of 3. So that's what it looks like. Now, this graph of f is translated 1 unit to the right and 2 units down. So in other words, 1 unit to the right and then 2 units down, right? So in other words, the original vertex here gets moved 1 unit to the right and then 2 down. So there we go. So in other words, this will be that new graph, right? It's there's no stretching because they didn't say anything that they just said there's a translation, 1 unit to the right and 2 down. So write the coordinates of the vertex of graph G. Well, it's 1 unit to the right and 2 down, so this is 1, and that's -2. So the coordinates must be 1, comma, -2. Express G in the form of 3x minus p squared plus q. Well, we just sort of did it, right? Because if this is our original function, so let's say g of x is simply, we're taking the original function f of x, and what are we doing? We're moving it 1 unit to the right. And 1 unit to the right is simply x minus 1, and then 2 down, -2. And remember, all we're doing when we have these functions is we take this argument right here, and you plug it right into the x over there. Okay? So what that means is this is equal to now, f of x is, so there's a 3, and instead of the x squared, right, it's something squared, and what that something is simply x minus 1. And it's -2 as well over here, so -2. So this is how we write it. So g of x is now simply 3 of x minus 1 squared minus 2. And we know that also because that's the new vertex. We can write that as 1 unit to the right and then 2 down. So that's how we get that. The graph of h is the reflection of the graph of g in the x-axis. Write down the coordinates of the vertex of h. So this red one is g. So I think, you know what I'll do is I'll sort of draw it again, and I'll draw it in red. I'll draw it in red, so here we go. So 1 unit to the right, and then 2 down. So that's -2. Here we go. And so there's some graph that looks like this. Okay. So there's some graph that looks like this. Now, there's a reflection, the graph of h. So this is g. This is g of x. Okay. The graph of h is a reflection of the graph in the x-axis. So in other words, if it reflects across the x-axis, use a different color. If it reflects over the x-axis, it should look like this. It should look exactly like that. Okay. So if it reflects like that, we know this point is 1, -2. So if it's reflecting right there, then that point should be 1, +2. Okay. So write down the coordinates of the vertex of h, which, and this is h. This is h of x. It's going to be 1, 2. Okay. Another way to do it is we can just use our x and y's that we've used before. So say for example, we have x, y, and we know our vertex is 1, -2. It's 1, -2. Now what they're saying is that there's a reflection across the x-axis. So if there's a reflection across the x-axis, really what has been transformed is that all the y's get changed, right? So in other words, there's -y, but the x's stay put. So if I look at this, x stays the same, so it's 1. And then it's what's -y, so negative of -2 is +2, so it's 1, 2, which is the answer that we have here. So you can do two ways. You can draw a graph and maybe get a visual interpretation, or if you want, you can just do it through algebra, just like how I did, and that's how you can also get the coordinate. All right, so let's do this. Let f of x equals x squared and g of x equals 2 of x minus 1 squared. The graph of g can be obtained from the graph of f using two transformations. So in other words, we're going from f to g, right? And if this is x squared and we're going to there, I can immediately say that there's a vertical stretch of 2 and a horizontal translation of 1 to the right. So just by looking at that. So I'm just going to write VS for vertical stretch, but remember, that's not how you should write it on a test. So a vertical stretch by 2 and a horizontal translation to the right by 1 unit, okay? So horizontal stretch to the right by 1 unit, and because it's x minus 1. All right, so the graph of g, so this graph g, is translated by the vector 3, -2 to give the graph of h. The point -1, 1 on the graph of f is translated to the point p on the graph of h. Find the coordinates of p. Okay, so this seems like a lot of information, but it's actually quite simple, okay? So if you observe, we have f, and then we get g, and then what they're saying is that this graph of g is translated by, there's some other translation to give h. So in other words, we're going from f to g, and then from g to h, okay? So let's basically see what's happening here. So let's say, I'm going to write over here. So here's f, And basically our xy plot over here, just for this one point, is negative 1, 1. Okay, so negative 1, 1. So let me just write that a little better. So negative 1, 1. Okay, so this is f. Okay, so how do we go from f to g? Well, we just said it. There's a vertical stretch by 2 and a horizontal translation right 1 unit. So so in g, it would map out to xy. So oops, sorry, that's not right. So in g, it would map out to, right? So what we said is vertical stretch by 2. So in other words, there's 2y, and a horizontal translation 1 to the right. So it's x plus 1. So this point would be negative 1 plus 1, so that would be 0. And then 1 times 2, so that's 2. But we're not done, because we still have to get to h, right? And there's another translation that goes from g to h. And so what is it? How do we go from g to h? Basically, if we have h, so in other words, what we're doing is we're moving 3 to the right. So it's x plus 3, and moving down 2. So it's y minus 2. So if we're doing that, then 0 plus 3 is 3, and 2 minus 2 is 0. So the coordinate of p, which is on h, is simply 3, 0. Okay, so just keep in mind that this is a very interesting question, because usually we just do one transformation, but now we're transforming from one function to another, and then there's another transformation that goes from this function to that. So we take the original point, we transform it to g, and then we figure out what the transformations are to go to h, and then we just transform those points again, and that's basically how we get our answers 3, 0. Okay, I'm just going to erase this part because I need some room to do the other part, but you can always look back, scroll back in the video and see how we got that answer. Okay, so here's some function, looks like that. They're telling us that there's a maximum point at a and a minimum point here at b, 3, negative 9. So the first thing that we have to write down, and pay attention to this, this says write down, which usually means that it's a very easy question. So the image of b after a reflection in the y-axis. So if we reflect this in the y-axis, how would it look like? This would kind of look like it would sort of look like the opposite. So it would look something like, and it would intersect right there. It would cross it right there and like that. So if this point right here is 3, negative 9, when I reflect it across that point, it would be negative 3, negative 9. Because what happens is that the y's stay the same, but the x's change. So the image of b is simply negative 3, negative 9. All right? So that's for number 1. Okay? What I'm going to do, okay, so the image of b after a translation by the vector negative 2, 5. All right? So, I could draw it, but I think that will just take me some time. So what I'm going to do for this question is I'm just going to do it like the x, y as we usually do. So the point is 3, negative 9. And we can see that it's x is being moved to the left by 2. So in other words, it's x minus 2. And the y's are being pushed up by 5. So this is going to be x minus 2, so that's going to be 1. And negative 9 plus 5, so that's going to be, negative 9 plus 5, so that's going to be negative 4. So 3 minus 2 is 1, and negative 9 plus 5 is negative 4. So the coordinate for this one over here, the answer to this one is 1, negative 4. Okay, so there's that. Okay, now the image of b after a reflection of the x-axis followed by a horizontal stretch with a scale factor of half. Okay, so if we look at it, let's look at the same thing again. So there's, 3, negative 9. And what they're telling us is that there's a reflection in the x-axis. So if there's a reflection in the x-axis, what that means is all the y values get multiplied by negative 1. So it's negative y. And there's a horizontal stretch by a scale factor of half. So if there's a horizontal stretch by a scale factor of half, what that means is simply all the x's get multiplied by half. So this will simply become 3 times half, which is 1.5. And negative 9 times negative y is, or negative 1 times negative 1 is simply 9. So the coordinate here is going to be 1.5 times 9. And that's it. Okay, we have a few more questions left. Part of the graph of a function f is shown in the diagram below. On the same diagram, sketch negative f of x. So in other words, all what we're doing is a reflection across the x-axis, because that's what that means. So if you're not comfortable just doing it by hand, the safe way is just get a few points. So I just like to pick the points where things are, where inflections are happening. And also the start and end points. So that coordinate, for example, let's get that. So that is -1, -4, -1, -4. This point is 2/2, so 2, 0.5. And the last point over here is 4, -1.5, so 4, -1.5. So if I transform it, remember it's negative f of x, so basically all the y's change because it's a reflection across the x-axis. So it's negative y. The x's stay the same. So it's -1, 2, 4. And this is going to be 4, -0.5, 1.5. So all we have to do is plot this now. So -1, 4, -1, 4 is there. 2, -0.5 is going to be, actually, you know what, I'm going to use different colors so I don't confuse it with the green. 2, -0.5 is there, and 4, 1.5 is right here. And I'm sure you can see it. You can see how this is sort of changing. So there you go. There you go. So that's basically the graph of that one. So we're done with that. Switch back to green. So let g of x equals f of x plus 3. So find g of -3. Okay, so this is one of these really interesting ones. So we want g of -3. So if we want g of so first of all, before we even do this question, observe that g of x is really f of x moved to the left by 3 because it's x plus 3. Okay, so if we want g of -3, if we want g of -3, it's simply f of -3 plus 3. All I'm doing is I'm plugging this negative value here and I'm plugging it right there. So it's f of -3 plus 3. So it's simply f of 0. And what's f of 0? This is our original f. So f of 0 is right here. And we can also, I could have taken that point and plugged that in there, but f of 0, because this black line is 0, is the original function. F of 0 is right here, which is -1.5. So this is simply equal to -1.5, and that's our solution. Describe fully the transformation that maps f to the graph of g, right? So basically we're going from f to g, and as we can see, that the transformation is simply a horizontal translation 3 units to the left. So I'm just going to write ht, but you're going to write horizontal translation on your test. Left 3 units. Okay, so that's number 10. Let's look at this one. This is a really good one. On the diagram below shows y equals x squared and y equals 5 minus 3x minus 4 squared. The graph of y equals x squared, so this graph right here, may be transformed into the graph of this one right here by these transformations. A reflection in the line y equals 0. So in other words, a reflection across the x-axis. A vertical stretch with a scale factor of k, a horizontal translation of p units, and a vertical for q units. Write down these values, k, p, q. Okay, so the first thing to do really is when you see an equation like this is always rearrange it in, I guess, like what I would call a proper form. So this is not proper form because the constant's in front, and then here's the coefficient and here's the quadratic part. So what I like to do is change it. So this is simply -3 x minus 4 squared plus 5. Okay, so that's there. So now from here I can pretty much read what's happening. So this negative is basically that reflection right here. It's a reflection across the x-axis. This 3 is the vertical stretch. So right away I know k is equal to 3. Now a common mistake a lot of students make is that they might think that k is equal to -3. That's not true because k is always going to be positive. The negative part is really associated with the reflection. So the reflection is what causes the negative, but the 3 is really the stretch itself. Next, there's a horizontal translation of p units. So this is the horizontal translation, and it's 4 units. So basically, p is equal to 4. Okay, and a vertical translation of q units, that plus 5 is the vertical translation, so it's equal to 5, and there we go. So always rearrange it into what I would personally call proper form, proper vertex form, and that just makes it easier to sort of interpret what the vertical stretches and horizontal translations and vertical translations are. Number 12. The following graph diagram shows y equals f of x. So here's our function. It has a min and max points at 0, 0, and 1/2. Okay. So on the same diagram, draw the graph of f of x minus 1 plus 3 over 2. Okay. So again, the easiest way is always with the start and end points and any sort of points of inflection where it sort of changes changes shape or changes direction. That's what you want to get. So here's our xy. Okay, so this is what would that be? This is it's almost like it's negative 0.8 and 2. So negative 0.8 and 2. This is 0, 0. This point here is 0, 0. This point here is 1 and 0.5. And this point here is, I would say, 1.8 and negative 1. So 1.8 and negative 1. Okay, so that's our original function. On the same graph, draw f of x minus 1 plus, okay. So basically, how would this interpret? How would this actually change? So what this means, it's a horizontal translation to the right by 1. So in other words, this will be x plus 1. And this is a vertical translation up by 1.5. So this is y plus 1.5. So what I'm going to do is, so this is negative 0.8 plus 1. So this is going to be like 0.2. 0 plus 1 is 1. 1 plus 1 is 2. And 1.8 plus 1 is 2.8. Okay. Now 0.15, so this is 3.5. 2 plus 1.5 is 3.5. 0 plus 1.5 is 1.5. 0.5 plus 1.5 is 2. And negative 1 plus 1.5 is 0.5. So what we're going to do is just plot this. So let me do this over here. So 0.2 and 3.5. So that's going to be right there. Okay. 1 and 1.5. So here's 1 and 1.5, which is right there. Okay. 2 and 2. So 2 and 2. And then 2.8 and 0.5, which is somewhere around there. So all we have to do is just connect the dots now. So that goes like that, goes like that, goes like that. So that's basically how you draw the graph of that. So you could have done it, your way too. Basically, you could have sort of figured out intuitively where it should go, but I like to be a bit more exact, so that's how I've done that. Okay, so what are the coordinates of the minimum and maximum points of this function? So basically, we already know because the minimum point right here is 0, 0, and it maps to 1 and 1.5. So for the minimum, I'm going to say that it maps to 1 and 1.5. 1 and 1.5. And if you want, you can just read that off the graph. You can see 1 and 1.5 right there. And for the max, we can see, because this was the max, 1 and 0.5, and that maps to 2, 2. And we can also see that on the graph here, 2, 2. So the max is at 2, 2. And that's how we do that one. All right, so 13 should be, okay, so the sketch shows part of y equals f of x, which passes through the point A, B, C, D. Okay, so these are all the points. Okay, calculate, here, a second function is defined by this. So as we can see, g of x is really f of 2 times f of x minus 1, which in other words is a vertical stretch by 2 and a horizontal translation to the right by 1. Now calculate g of 0. So g of 0, so let me just do this here. I'm going to do this. So g of 0 is basically equal to 2 times f of 0 minus 1. So it's 2 times f of negative 1. And if we look, what is f of negative 1? F of negative 1 is the value of let's see, 1, 2, 3, 1, 2, 3. It's a value of 3. So it's actually 2 times 3. So it's equal to 6. So g of 0 is 6. So we've done with that one. Let's do g of 1. It's the same concept. We're going to do 2 times f of 1 minus 1, which is 2 times f of 0. And what is f of 0? F of 0 is 2. Okay, f of 0 is 2. So 2 times 2, which is equal to 4. So g of 1 is equal to 4. Okay, g of 2 is equal to same thing. So 2 times f of 2 minus 1, it's equal to 2 times f of 1. And f of 1, if you observe here, this is f of 1, its y value is 0. So it's basically 2 times 0, which is equal to 0. And finally, g of 3, I'm going to do g of 3, I'm going to scroll down a little bit. Okay, so g of 3 is equal to 2 times f of 3 minus 1, which is 2 times f of 2. So since this is our original function f of 2 is equal to 1, because here's the x value is 2, the y value is 1. Okay, so it's equal to 2 times 1, which is equal to 2. So we got that. Okay, so here's basically one sort of method of finding what g of 0, g of 1, g of 2, g of 3 is. There's also another way, which, basically our standard method of how we do things, which is, let's just say we have our xy plots. If we take our xy plots for these ones, we've just been given these 4 points, or 5 points rather. So x, y, and so we have -1, 3, 0, 2, 1, 0, 2, 1, and 3, 5. Okay, so that's basically on the original function, and if we transform it, so this is f, and then we're going to g. If we transform it, we can see it's a vertical stretch of 2, so it's basically 2y here, and translation 1 to the right. So if we transform these, this will become 0, 6, 1, 4, 2, 0, 3, 2, and 4, 10. Okay, so this is our g function. So these are x values and these are y values for the g function. So if we want g of 0 is 6, which we have right there. If we want g of 1 is 4, which we have right there. If we want g of 2, it's equal to 0, which we have right there. And if we want g of 3, we have g of 3, which is 2, which, let me scroll down, we have right there. So that's also another way of doing it, but keep in mind that if they're asking for g of 0, don't look at f and see how it maps or anything. Look at g and see where x is 0, and then basically just write down what the y value is, and that's really it. Okay, so on the same axis, sketch the graph of g of x. Well, this was really useful when we wrote these plots, so let's basically use this. So this is 0, 6. So 0, 6, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So that's that one right there. 1, 4 is right here. 2, 0 is right here. Okay. 3, 2 is right here, and 4, 10. Oh, we don't have enough room. But anyways, 410 will be basically something up, like really high up here. And also, one other thing is, we started with point A. So, like, if we connect these dots, let me just connect these dots right here. Okay. It sort of doesn't really look like that one because we don't have this point. So this point is -3, 0. So let me just put another point here, -3, 0. And let me transform that. So that point will be -3 plus 1, so that's -2. And 0 times 2 is 0. So basically it'll come down to -2. So in other words, this will end up looking like that. Oops, not the best graph. Oops, what happened? Oh, sorry. My just got disconnected for a second. So this one, I need some more room. Sorry, if I connect these two right here, okay, it's not the smoothest, but basically you get the idea that it's being stretched by 2, and then it's being moved to the right. It's being stretched by 2 and then moved to the right by 1. So that's basically what's happening over there. So this point right here is 5. It should really stretch to 10. We don't have room, but that's sort of what it looks like. So we've done A and we've done B. Okay, let's do the last one, which is the following diagram shows part of f of x with the vertex, so with vertex v. So this is our f of x. As they said, it has a vertex 0, 5 and with the v. So this point right here is 0, 5. And its image, y is after a translation of hk, has the vertex of t, 3, 6. So this is 3, 6. Now, one thing I'm going to do whenever you see something like this, before you even sort of read the question, is always rearrange this. So this is not like what I would call in standard vertex form, because I like to just put the x squared part first. So I know there's negative x squared, and this is going to be plus 5 because this is positive 5. So it's negative x squared plus 5. Okay, write down the value of h and k. So in other words, what is this translation vector? So if you observe, this is 0, 5, and it's being moved to 3. So in other words, we're moving 3. This distance right here is 3. Okay? So h right away is just a horizontal translation, so this is equal to 3. Now the next question, if my vertex moves this way, how far up does it move? Because that's going to give the value of k. So it has a y value of 5, and then moves up to 6. So in other words, it goes from 5 to 6. So the change there is really just 1. So it's just moving up by 1. So k is equal to 1. Okay? Now, write down an expression for g of x. So this is our f of x, the original one, and this is our g of x, the transformed one. So one thing you can do is, we know that all we have is just a horizontal and a vertical translation. So g of x is really f of, now it's moved to the right by 3, so it's going to be x minus 3, and then it's plus 1. Okay? But that's not what they want. They don't want it in terms of f of x, they actually just want an actual expression. So if you recall, what we usually do in these cases is, here, I'm going to write this f of x right here. So f of x, now originally like they wrote 5 minus x squared. I don't like that, so I'm just going to change it to negative x squared plus 5. So what we're doing is really just taking this argument right here and just plugging it in right there. Okay? So what this will equal is simply, it's going to be negative, right? And then into that x is x minus 3 squared plus 5. Don't forget that plus 5 because that's still part of the f of x, plus 5. And then there's this plus 1 added at the very end. Okay? So let me just use blue. So this is really this part right here. And you're replacing the argument x minus 3 into x. So that's why this negative comes from there. This x minus 3 is really just this argument right there. That square comes from here. This plus 5 comes from there. And then finally, don't forget that we have this plus 1 that we added on, so it's plus 1. So we're not done with this yet. So this is equal to negative x minus 3 squared. And what's 5 plus 1? It's plus 6. So that's the solution for B. Okay. On the same diagram, sketch y is equal to g of negative x. So this is our g, okay, and we have to sketch y is equal to g of negative x. So what I'm going to do is I'm just going to erase some numbers and things like that. But this is our g, so let me actually get this original g in red. Or no, in red. So, so this is the original g. Okay, this is the original g. Now, if it's y is equal to g of negative x, what that means is a reflection across the y-axis. So if it reflects across the y-axis, this point right here will stay the same. So I'm going to use a blue color in right now and just show the reflection. So it's going to reflect like that. Right. So in other words, this red, if I reflect across the y-axis, is the blue one right there. And if this point as they told us, was 3, 6, then this vertex right here must be, remember the y's don't change, it's only the x's that change, so it must be -3, 6. And so that's how we get that. They didn't ask for this, I was just trying to show you that. On the actual test, you would just graph the blue line and you wouldn't even write the vertex. Yeah, don't ever add extra information that they don't ask for. And that's basically the solution set for the transformations package. All right, so good luck on the test, and I'll see you in the next video. Bye.